Hello everyone, welcome back in the course of higher surveying. Well, we are in the module 2 and this is our third lecture of module 2. So this lecture is projected coordinate system. In the previous two lectures we learned about how to establish a reference frame, how to establish a reference system, how to conceptualize a reference system, how to establish a reference frame, that is a realization of a reference system, and later we decided that how can we use the coordinate system or different type of coordinate system to locate one point or multiple points. Well, this was the good background for us to understand different kind of coordinate systems and reference frame for the earth. Remember that earth requires a different set of coordinate and reference frame. Why? Because it is no more a plane surface. It is a curvilinear planet. Okay, in the lecture 2 we realized that how to develop a transformation between the local reference frame to geocentric frame or maybe geodetic frame. Later we also realized that how to convert a geodetic frame to geocentric frame using datum transformation and so on. So there we defined two terms, coordinate transformation and reference frame transformation. Reference frame transformation, where we change the definition of reference frame from one to another, and that we also called datum transformation. In case of coordinate transformation, we are not going to change the reference frame or the ellipsoidal surface. Okay, so that was the understanding we have already developed. Now in this lecture of this module, projected coordinate system, where we are going to project the curvilinear surface of the earth on a plane surface. Remember, in the first lecture we have criticized this approach. Again we are going back. What could be a reason? There are some valid reasons for that, and this time we are going to do it for a very large area, not for a small area. Remember, for a 10-kilometer length on the surface of earth, it can be understood as a flat line also or flat plane also, because the distance or the difference of the distance between the 10-kilometer curvilinear length on surface of earth and the 10-kilometer distance along the line of collimation only have a difference of some millimeters. And for that reason we assumed in a plane survey that we can use the projected coordinate system, or we can assume the flat plane of my reference frame for planimetric coordinate system. Well, so that was our preparation, but later on again we are going to do the same thing. However, we are this time doing for a very large area, for maybe some hundreds kilometers or so. Okay, but before that we should understand what is the requirement of doing that. So let us go into this lecture. First of all, sometimes the two-dimensional information is sufficient for me. Okay, I don't need the 3D information. And the first example is georeferencing. Georeferencing is a process of assigning the coordinates to a image, satellite image or camera image or aerial image. Here I would like to give you a brief introduction about that. You might have done it, or if you have not done it, no problem. Just understand it is an example of a coordinate transformation, where I am assigning the coordinates of a map to the image. So what will I do? I'll select the common points between the image and the map. That means for a given area I have already an image with me. It could be satellite image, it could be aerial image, or it could be terrestrial image. That means it is an acquired image from some camera. Okay, now I will identify some features on that, and I will identify the same features on the map. From the map I will take some coordinates of those features, and I will assign those coordinates of the map to the same features in the image. Then I will rotate that image into the map coordinate system. Well, that's a very simple process. But here if you look at, I just want to do a two-dimensional coordinate transformation, or where I am using only x and y coordinate of the map as well as two-dimensional coordinate of the image, that is pixel coordinates, row and column. So it is kind of two-dimensional coordinate transformation going on. That's the first requirement for this particular case of georeferencing. We understood that we don't need the third dimension, because after doing the georeferencing of map, I am going to classify my map. That means I am going to identify which area is forest, which area is agriculture, which area is sand, which area is a river, and so on. So for that purpose I do not need the third dimension or the third information on the map. Fine. The second is 2D curvilinear coordinates, that is longitude and latitude. Sometimes they itself suffice the purpose or they are sufficient. For example, another good example is visualization. In case of visualization, it's very important to understand latitude and longitude. Why? Because if you remember, in case of geocentric coordinate system, well, I said before also, it is good to work mathematically or computationally. But when you just imagine that if I give you some kind of 3D information, let us say capital X, capital Y, capital Z of some point on the earth. So there is a complete tuple X, Y and Z, and I ask you, can you please identify the position where this point is indicating on the surface of earth? Extremely difficult. Rather, it is impossible to comment. Okay. So, but if you look at the longitude and latitude, if I say the latitude of a place is almost around 21 degree and longitude of the place is 91 degree or 91.5 degree. You can say, yes, this place is somewhere around Guwahati. How could we imagine this thing? Because you know that there is some 0 degree longitude. If you take a kind of curve here or kind of angle here which is equal to longitude 91 degrees, and then you will take from this horizontal equatorial plane, if you take this angle, vertical angle along the latitude line or along the meridian line, and if you measure around 21 degrees, if you imagine, it's very easy for visualization that you are somewhere near to the Guwahati. But for that purpose, you don't need the third dimension, that is the height. And if I further add it, let's say that wherever place I am indicating by 91.5 degree and 21.5 degree, this kind of longitude and latitude, if I say the place itself has a height of 55 meter, an ellipsoidal height or maybe orthometric height, then you come to know with respect to some ellipsoid, this place is 55 meter high. The third information is not going to make any change in the place identification. Well, it will certainly add some information which sometimes is very important, but as far as identification is concerned, you don't need the third dimension. Thirdly, I have high accuracy requirement for my sum of the work. Now, at some times I don't need it. Just take an example. Today evening you want to go with your friends for some recreation. So as a result, you want to go to some restaurant to celebrate some party. Okay, so what will you do? You know that there is a restaurant and it's very famous in your city, but you do not know how to reach there. So what will you do? You will take your smartphone or mobile phone like this, and then in your mapping services you will apply a position, or you will use two positions. One is your own position at your home, and second one is the destination, that is restaurant. Okay, you give the name and your map service will give you shortest route along the map, and then you will start using a GPS. So GPS will tell you your position when you are moving. Okay, now let us see, you are about to reach to that restaurant. Okay, fine, and that restaurant is on the left hand side where you are already moving, because we have some left hand system here in India where you are moving on the left hand side of the road. So around 3 to 5 meter or 10 meter, you will come to know, yes, you are about to reach to the restaurant. So do you need at this stage a kind of centimeter level accuracy to reach there? Absolutely no. You are very comfortable with 3 to 5 meter accuracy also, because your purpose is to reach the restaurant. Once you are around the restaurant, you will just look at this restaurant and you will enter into that. So you need identification of the place in this case also. That means what are the surroundings. So what will you do? You will look at the surrounding of the restaurant and you try to figure out where the restaurant is when you are very close to that. Let's say within 5 meters. I think within 5 meters you can directly see the restaurant also very easily. So what information you need here? If the restaurant is on the left hand side of the road, it should be shown on the left hand side of the road on your map. Or if it is on the right hand side, it should be shown on the right hand side of the map. That is it. And if I assume that if there is a 2-lane road which is 3.5 meter each lane, which is generally the dimension, so 2 to 3 meter or 4 meter accuracy is sufficient for you. So with this idea, we know that at times we don't need high accuracy. Rather, we need to have some kind of coarser accuracies like 2 to 3 meter or 4 meter. So with this understanding, if I use a projected coordinate system, there is no harm. I am very comfortable. Secondly, it is very easy to develop such applications also related to projected coordinates. Okay, that are the few reasons. They are not the only reasons. They are the few reasons why we need map projection. One more example I can give you. Just imagine if you are a sailor like Vasco da Gama, who is sailing in the sea from one country to another country, right? And so you are going from one country to next. Then what will happen? Once you reach to a place, you don't need more than 10-meter accuracy. In that case, fine, map projected coordinates are okay, or the map projection is also okay with you. At the same time, you need a map of very large area. That means since you are crossing the sea or ocean. Well, I hope that you understand the message that in this course, when we talk about map projection or the projected coordinates, we are going to do it for a very large area, so that I will have an understanding of very large area, for example, a city, a state, or maybe a country. Well, so let us look what is a map projection. So map projection is a mathematical function relating features on curved surface to features on a plane. That means I have a two-dimensional coordinate system, that is lambda and phi, longitude, latitude, and I am converting them into some Cartesian coordinate x and y using some function or some transformation. Okay, you may ask, why should I convert it when I know that lambda phi is very convenient to use? There is a reason for that, and the reason is, I ask you, okay, go 2 degree east and then go 2 degree north in the line of meridian and report me where do you reach. Very difficult. I think if you even assume that 1 degree is equal to 1110 kilometers, so you may think first of all how to go 1110 kilometers, or 2 degrees means almost 220 kilometers in the east direction. Okay, then going in the north by again some degrees. Very difficult, very inconvenient. Take this map and go along the east direction by 100 kilometer or by 10 meter or maybe 10 kilometer. Pretty easy for you, and that is why we do the map projection. That means we convert the longitude and latitude into Cartesian coordinate x and y. Okay, we already know that accuracies are not there, or rather we are compromising on the accuracies because of the projection. Okay, one more information I would like to share with you at this instance. When I express the longitude and latitude, which is only two-dimensional coordinate system, it is also called geographical coordinate system. Okay, so first projected coordinate system is I am showing you here. There is a plane of projection which is shown here, and there is a ellipsoid shown here. Okay, one more thing is there, that we are just showing ellipsoid, that since we are not going to use the height, that is ellipsoidal height, we are going to drop it. Okay, even you can assume if there are 2 points, which is not possible to have at one location, at one longitude and latitude, a point can vary in height. That means it can be 55 meter or it can be 100 meter. But at a given lambda phi, you will have only one point on the surface of Earth. Well, since we remove this information, so the point which is lying on the surface of Earth, now it is lying on the ellipsoid. Okay, you can assume like that. Fine. So before we go ahead, there are few terms. For example, latitude, what we call as parallel of latitude. Since the latitude A, that means it is a parallel of latitude, where latitude is not going to vary and it will remain same as shown by, let's say, latitude A. Same way latitude B, latitude C is there. And then we have a graticule. The graticule is the box formed by the intersection of meridian lines and the parallel of latitudes, or I can say latitude lines. So this is one graticule. So there are many graticules shown on the ellipsoid. Okay, now let us say there is a light source which I put at the bottom of south pole of the ellipsoid, and now because of the light source, what will happen, all the lights will go like this and they will project the points on this plane of projection, and because of that you will get some kind of figures. So let us try to make those figures. So since the light is exactly below the south pole will appear as a dot like this, shown in the figure on the plane of projection. Okay, the next, that is parallel to latitude, will appear like that, circle, because it's a kind of circle here and light is projecting on this thing. Third, latitude B, latitude C. Now I have projected, and maybe ellipse I can also show the equator. But what about the other meridians, which are vertical lines passing through north pole to south pole, right? And they are also touching the equator. What about those? They will appear as a straight line. Now you can imagine that there is a light source which is projecting the straight lines or the curvilinear meridian lines from the south pole to diverging out. So hence I will have this kind of lines. Okay, what about the graticule? So this is my graticule here. Well, I hope that you got the idea what is map projection, and you can now develop your own map projection, or you can imagine if I give you where is the light source, how ellipsoid is placed, and where my plane is placed. So once three things is clear to me or clear to you, to anyone, we can imagine how a map projection is developed. I call map projection or the projected coordinates. The better name is map projection. You can observe here that areas are distorted. For example, I am showing you a graticule. It is now distorted in the map projection. Same way, length is also distorted. That means the length is no more a true length which is on the surface of ellipsoid. It is no more reflected as a true length there on the map projection. Shape is also distorted. That means the angle between the two lines, I can say the angle between a latitude line and meridian line is distorted now. Direction distortions, that means the azimuth of a line is also distorted from the ellipsoid when it is projected to the map projection. Well, so we have understood what are the drawbacks or what are the limitations of map projection, but still with these given limitations we would like to use, because they provide some kind of facilities which are not available otherwise. I am projecting the surface on the plane, that is the map projection. I place an ellipsoid into a cylinder which is so big, covering the whole earth or whole ellipsoid. So those points which are lying on the ellipsoid I projected exactly on the surface of the cylinder, and now I cut the cylinder and I unfold it. Okay, you can imagine there is one wrapper like a paper which is of shape cylinder, and now you are projecting your ellipsoid onto that paper and then you unfold it again. So how will it appear? Let's look into animation. So let us say I have cut down the cylinder and then I am unfolding it. So since all the projected points which I projected on the surface of cylinder, now it will open like this, like unfolding a book, or rather you are unfolding a cylinder like this. So this is what is cylindrical projection, and which we are doing on a curvilinear surface. Similarly, instead of cylinder I can also use cone. Well, in case of cone, I will cut a cone from its lower edge to the vertices and then I will unfold it. Okay, so let us look all this thing into coming slides. So the general properties of projection system is conformality. That means I want to preserve the shape of the map. Okay, well, what is the shape on the map? Remember I told what are the distortions. Similarly, out of those distortions, at least I would like to ensure one property should be secured. That means if I want to secure conformality, that means I am going to maintain the same angle between the two lines before projection and after projection. So let us see if there are two lines at 90 degree before projection. After projection, they will maintain the same angle in the map, and hence I will say this is the conformality property. That means the map is a conformal. Okay, what about the equivalence? Equivalence is preserving areas. That means the size of area is same before and after. Distances, if the length of a line between 2 points is same before and after the map projection, well, that's called distance preserving, or sometimes we call it scale preserving also. Direction, if azimuth, that is the line with respect to the north direction, is preserved, then we call it the direction preserving map projection. Okay, a map projection can ensure few properties, and sometimes it does not ensure even one. None of the projection can ensure all the properties. So they may ensure few of them and they compromises on the other. So let us see the classification. So it is based on the projection surface. So as I shown you before, planar projection, that means the plane of projection is plane. Okay, conic projection, if plane of projection is conic, and then cylindrical projection if projection surface is a cylindrical. Further, we have pseudo cylindrical projection. Remember, I gave you an example of pseudo. What's the mean? In the movie, there is one character who looks like exactly the main character or the hero, but he behaves slightly different. So such a thing we call it pseudo. So there is some projection which looks like cylindrical, but it does not fulfill all the criteria of the cylindrical projection, but still we call it pseudo cylindrical projection. We are going to look into all these kind of projections into this lecture. Okay, in case of azimuthal, stereographic, gnomonic, orthographic, they are the names. In case of conic projection, LCC, polyconic, equidistance, conic, they are the examples here. Cylindrical, we have Mercator, transverse Mercator, oblique Mercator, and then Robinson's and sinusoidal equal area projection are the example of pseudo cylindrical. Well, in this lecture we are going to look at few of them and their transformations between the two. So there is a distortions as we discussed. So distortions of map projections are affected by the imaginary light, where we put the light, remember. Okay, so we have orthographic, stereographic, or gnomonic projection. They have different point of light source. Then orientation of map surface, that is where I place the plane of projection. Okay, one term is called tangent and one is called secant. If my plane of projection cuts the surface of Earth, I call it secant. That means it is going to touch at two places in case it cuts. But if it is touching at only one point, for example cylinder is touching at equator only, then I call it tangent. We are going to discuss few of the map projection system here. Okay, so let us go one by one. First, azimuthal projection, where the stereographic projection is there. In case of stereographic projection, I have a light source exactly at the south pole, and it is trying to project the area of ellipsoid above equator and equator. So there will be equator that is going to be made as circle after projection. Okay, and all the latitude or a parallel of latitude above equator, they will be appearing as circles, as you can show in the figure. Okay, what about the north pole? North pole will be appearing as one point because the light source is exactly below there. Fine. So there on the right hand side we have shown one example of how will map look like if I am using a stereographic projection for surface of Earth. There are some properties in this map projection. We ensure that this map projection is conformal. That means deliberately it is ensured that the two lines, if they have some angle theta between them, the angle between them should remain theta even after projection, and because of that we call it conformal property. So after ensuring this conformal property, we get some features like directions are true from the central point of projection, the north pole, because it is central point of projection was north pole. So from the north pole all the directions are preserved, in a sense directions are true. For example, if I take all the meridians, the angular distance between the meridian before and after, they will remain same. The scale increases away from the center point. If I go away from the north point or the center point of projection on the map, then the shorter distances will be shown by the longer distances. Okay, any straight line through the center point is great circle. Okay, now you can imagine that all the meridians which are great circles, they are originating from the north pole, they will appear as a straight line because they are bifurcating out from the north pole like this. Distortions of area and large shapes increase if away from the center point, because as I said that distortions of the lines are increasing as we go away from the north pole. So automatically areas will also be distorted because area is a combination of two lines in different direction. Okay, what's the use of this map? Such a map is used for geophysics to solve spherical geometry problems and for mapping of polar regions. Now you can imagine that this stereographic projection, it is not distorted at the north pole. Why? Because north pole is completely intact there or completely projected without any error, and as a result I should use it for the polar regions. In case of south pole, I will put the light on the north pole and I will project all the light rays from the north pole towards south pole, and I can plot the map like that. So that's the idea here, that we want to have minimum distortions, and as a result we use a certain type of map projection in certain area of Earth only, and that's the reason we have lot of projections, and we have to understand which projection is appropriate for which area. So that's the idea here of this lecture. So before taking any decision anywhere, if you go to some other country also, you should know that why this particular country is using particular type of projection. Well, let's go ahead. Next is gnomonic projection, which is again a planar or azimuthal projection. Okay, here you see the light source is put on the center of the ellipsoid, and as a result it is not projecting the equator, or rather it will project the equator at the infinity, so that will not be visible in the map. So All other parallel of latitudes which are parallel to the equator are projected in the form of circles. Again, North Pole is again projected without any error, right? And now you see on the right hand side there is an example of gnomonic projection. The properties, again the map is perspective, that is direction is preserved. Directions from the North Pole, that is from the center of Earth to the tangent plane. Okay, so tangent plane is nowhere, it is at the North Pole, flat to the equator, parallel to the equator like this. So in this plane we have directions preserved. So what are the features if I ensure this property? So directions are true from the central point of projection, which is similar to the stereographic projection. Any straight line through the center is great circle. Distortions of areas and large shapes increase away from the center point. Okay. So now uses are used along with the Mercator projection for shortest path and seismic work, because waves tend to travel along the great circle. That's the kind of assumption seismologists make, and that's the reason we prefer to use it for the study of seismic work or for the earthquake studies and so on. Now we go to the conic projection. That's another class. In the conic projection, the first projection is Lambert conformal conic projection. Here you can see it is a secant type of system. That means it is cutting, the plane of projection is cone, and cone is cutting the ellipsoid at two places, at two parallel of latitude. These two latitudes are marked in red color. Now you can see these parallels where the cone is cutting the ellipsoid are called standard parallels. So in this case I call standard parallel 1 and standard parallel 2. Fine. If I look at how these are projected on the surface of cone, so you can see that the parallel of latitude which are appearing almost parallel to the equator in the circular form, when they are projected they are appearing as a curvilinear line on the map surface. So the same red lines are denoted by the red lines in the map projection, and some arrows are indicating how they are being transferred. Okay, that means once you project your map projection, that is ellipsoid, onto the conic surface, cut it, unfold the conic surface, it will appear like that. So wherever the projection plane touches the surface of ellipsoid, we will get minimum distortions. In the same fashion, since the cone is cutting at two, or rather it is touching the ellipsoid at two places, one is standard parallel 1 and another is standard parallel 2, so I will get minimum distortion at these two standard parallels. Okay, so directions are reasonably accurate. Distortions of the shapes and area are minimal between the standard parallels, but increases away from these. What is the meaning here? Let us see there are two standard parallels, and I told that at these standard parallels I will have minimum distortions. So let us see the standard parallel 1. So as I go away like this, I will have distortions. For this lower one or the standard parallel 2, as I go away I will have distortions. Now distortions between the two standard parallels will come to the maximum somewhere in the middle part. If I limit that maximum distortion to some limit, then I can easily utilize these two standard parallels or area between the two standard parallels for this map projection, and that is somehow an advantage of this. We'll see why. Okay, now what happens above this standard parallel 1 and what happens below the standard parallel 2? Here distortions are keep on increasing, well, and here distortions are keep on increasing, and I cannot limit them also by some way, and as a result it gives me some advantage for middle latitude country. We'll see why. Okay, the shapes on the large scale maps of small area are preserved. Now as I told that there is an advantage of this one for the middle latitude countries, because distortions can be limited to a certain value, and as a result between the two standard parallel, whichever countries are falling, I can use this map projection for those countries. Remember, in the middle latitude our country India also lies, and as a result of that the Survey of India topo sheets are having LCC projection. So even some countries which are extending in east-west, but at the same time they are lying in the middle latitude. Okay, there is some country which is area has like this along the east-west more, then and it is also falling in the middle latitude, maybe parallel to India or so, then we should use this LCC projection for that country also. So let us go ahead. There is another type of conic projection which is polyconic projection. So polygonic projection is like that. There is ellipsoid, and I have this cone which is touching at certain latitude. There is another cone which is touching at certain other latitude, and this is one more cone, and so I am representing here. You can see that there is a middle line here. This line, it is shown here, and that is not distorted, and because of this I can say along this particular meridian distortions are minimum, even there are 3 cones. Okay. Moreover, if I see that 3 cones are touching the 3 latitudes, or even if there is a 1 cone it is touching certain latitude, fine, there will be minimum distortion. So this is an example of the polyconic projection. So what are the properties here? First of all, no property is preserved here. So whatever mathematics we do with this projection system, we cannot secure or we cannot preserve any property here, but still we get some features like directions are true along central meridian, as we have seen that along the central meridian distortions are minimum. Distances are true along each parallel and central meridian. Well, still I am getting some of the things very correct. Shapes and areas are true along central meridian. That's good enough for certain purposes, and as a result it is used for the area with a north-south orientation, and here middle latitudes are not important. Okay, if it is a middle latitude, since we are using a cone, it's also fine, no problem. But most of the time for the country like India, which is expanding more in the north-south compared to east-west, this kind of polygonic projection is recommended. Now Mercator projection, that is a class of cylindrical projection, and we have already discussed in the animation. So let us see a little more into that. So there is a Mercator projection shown here. That means there is a cylinder which is covering the ellipsoid, and now I am going to project the ellipsoidal points on cylinder. Now there is a term called rhumb line comes here, and which is very important to understand. So a rhumb line has been shown here, and you can see that the rhumb line is maintaining the same angle with each and every meridian, and that's the advantage. This is the way we define the rhumb line. Okay, that means if you see this angle here and this angle with each and every meridian, it is same. So now let us look into the property of Mercator projection. Property is it only preserves the conformality property. Then distances are true along only equator within plus minus 15 degree. Now you can understand with conic projection and stereographic projection, as explained, if the surface of projection or the projection surface touches the ellipsoid, at that point we have maximum or a minimum distortions, or the maximum properties are preserved. So here, since the cylinder is touching the equator, around the equator we will have minimum distortions. So distances are true along only equator within plus minus 15 degrees. Equator and other parallels are straight lines. You can imagine on the cylinder they will appear as a straight line because they have been projected like that. Shapes within a small area is preserved. Any straight line on a map is a rhumb line, and directions are true along rhumb line. The rhumb line, as I told, it is maintaining the same angle with the meridians. Okay, now since it is a conformal, so you can find out the rhumb line will be a straight line. Okay, the uses are it is used for navigation of maps or equatorial region. That means somewhere if a country is around equator, we should use this Mercator projection for that country or region, and within plus minus 15 degree we will find minimum distortions. Coming to the transverse Mercator projection, now you can imagine I want to have the same properties for some countries which are not at the equator, rather they are off the equator along certain central meridian. So what will I do? I have tilted my cylinder from vertical to horizontal, and as a result now cylinder is touching certain central meridian or certain particular meridian over a country. For that particular central meridian, which I am calling central meridian, I can have within plus minus 15 degree minimum distortions. So now this is the property, it preserves the conformality property. Distances are true along central meridian. Okay, now you can imagine how nice it is to understand any map projection. Distance, direction, shape and areas are accurate within plus minus 15 degree of the central meridian, as I already told you. Graticule spacing increases away from the central meridian. What does it mean? As I shown in the first slide, what's the graticule spacing? Now if you go away from the central meridian like this, you will have more distortions in the reticle spacing or the area. Fine. It is used for mapping large areas that are mainly north-south extent. Now you can imagine easily why we are using transverse Mercator for some countries which are extended in north-south. UTM, what we call Universal Transverse Mercator, it is a particular type of or the specific example of transverse Mercator projection system. Okay, UTM is now most popular projection system which is being used mostly now, especially including GPS and GNSS services. Perhaps your map projection system that you are using in your mobile phones might be using UTM only. Okay, so in this UTM, the picture is shown. You can get a lot of literature about that. It's pretty easy to understand. So properties and features are like globe is divided into 60 zones, that is ellipsoid is divided into 60 zones, each of 6 degree longitude. So I have 60 such zones which are divided, each of width 6 degree longitude, 6 degree, 6 degree, 6 degree all along the equator. So it is extended from latitude of 80 degrees south to 84 degree north. That means these are the latitudes, these zones, vertical zones are extending from 80 degrees south to 84 degree north. Now I am dividing the zones in horizontal way also now, right? So these zones are divided into horizontal bands spanning 8 degree latitude. So what does it mean? There is 6 degree longitude zone and 8 degree latitude zone. Okay, so this is 8 degree span and this is 6 degree span. So now I have many such zones on the UTM map projection. Secondly, these projections are limited between 80 degree south and 84 degree north. Okay, so we are starting for this kind of bands which are 8 degree in the latitude span with the word C at 80 degree south, and there is a last word X at the last zone which is starting from 72 degree, and it is not 8 degree wide, rather it is 12 degree wide. Fine. So we can see here all this thing. And secondly, we have avoided the word I and O, which are generally used for input and output and many other things. So now we have so many zones and so on. Okay, what about the polar regions which is above 84 degree north and below 80 degree south? For those polar regions, we use stereographic map projection, but we have given on the similar fashion the name Universal Polar Stereographic Map Projection, again which is a specific example of stereographic projection. And there we don't use UTM, we use UPS there. Fine. Now you can understand very easily why UTM is so popular. Okay, what about the other meridians? That means suppose there is a great circle along which a country is lying in north-south direction. That means which is not along the central meridian, rather it is on the some other line which is shown here by red color. For example, if you see here where the dot is moving here. Okay, now for this oblique Mercator projection, I can ensure the same property by tilting the cylinder. Okay, since the cylinder is tilted, it is going to cut the ellipsoid at certain great circle. Okay, so a particular country which is having a great circle as a center of their line of the country, they will use this kind of oblique Mercator projection, and it has again conformal. Distances are true along the great circles, that particular great circle. Distances, direction, shape and areas are accurate within plus minus 15 degree of the great circle. Reticule spacing increases away from the great circle. Yes. Now you can imagine that 3 cylindrical projections, one is Mercator, then transverse Mercator and this oblique Mercator. They are more or less similar, but only difference is they are having different orientation. And what is the use? Used to show regions along a great circle. That means a certain country or certain area which is lying across a great circle, not across a certain meridian. Then we will use oblique Mercator projection for the region or area. Now let us come to the fourth category of map projection system, that is Robinson projection. In this projection, there is some meridian shown here, and this is central meridian. Okay, all these meridians are cut between 2 layers of a cylinder. That means there is cylinder here, and now I have cut it at 2 places, and between these 2 all the meridians are projected, and because of that we get this kind of map projection shown on the right hand side. Property: no properties in this projection is preserved. What are the features? Directions are true along all parallels and central meridian. Remember, there is one central meridian which is appearing as a straight line. So directions are true along all parallels which are like that, because they are also straight lines, and central meridian which is also straight line. So distances are same along equator and other parallels. Okay, scale constant along any given parallel. That means if I have a parallel which is straight line in the map projection, I will have same scale. So what is the use? It is used for the National Geographic maps and Goody's map. You can search more about that. There is another pseudo-cylindrical map projection where sinusoidal equal area projection is there. Okay, you can see these distorted lines of meridians here, 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 and so on. But this central meridian is straight line. So I expect that the properties along this central meridian should be preserved, or they will have minimum distortions. So no property is preserved here. Graticule spacing shows equivalence of area. That means whatever the area graticule was having, if they are projected on the map surface, they will have the same area, or they will have minimum distortions. Directions are correct along parallels and meridians. As you can see, shapes are distorted away from central meridian and near the poles. So this kind of projection systems is not used for the polar regions. Then what are the uses? Used for large area that are mainly in the north-south extent, but not in the polar region. Fine. Used for maps of Africa continent, e.g. for South Africa. Now we have a application called GeoTrust, as we have already explained it in the last lecture. Again, in this lecture, we are going to use it for the map projection. Rather, we are going to look from different perspective this time. So we have point data processing and batch data processing. So let us look into the point data processing and batch data processing for map projections. So we are going to cover the coordinate transformation with map projection as well as datum transformation with map projection. Now this is the GeoTrans interface, and well, this is the file, and how to format the units you already know. Okay, so let us go ahead. Okay, now I am showing you the point processing. Here we are showing a point processing for conversion of geodetic coordinate system to UTM map projection. So first of all, you will select here geodetic in the input, and then you are specifying your input coordinates like this. Okay, now in the output you will select UTM, and there you are doing now convert upper to lower. By doing this, you will get your answer here. So now you have coordinates in the UTM map projection. Okay, surprisingly, in the output and input we have same datum, that is WGS84, and so we are saying this is the coordinate transformation in the map projection. That means we are not doing any datum transformation now. Let us do the same thing in a reverse fashion. That means I am converting the point in the UTM map projection to geodetic coordinate system. So what will I do here? I will specify my input in the UTM. These are the further information on the coordinates easting and northing, and then I will choose geodetic in the output. Then I will do convert upper to lower, and it will give me the output coordinates. I hope you got what's the idea here for point data processing. And what about the batch processing, or what about the point data processing with other projection? Let us see geodetic coordinate system to LCC map projection. Same process you will follow, only in the output you will select the Lambert conformal conic projection, maybe with one standard parallel, that is tangent system, or maybe with two standard parallel. So example here shown with the one standard parallel. So on the left hand side I am converting from geodetic to LCC map projection. In the right hand side I am converting back from LCC map projection to the geodetic coordinate system. You can also try yourself, it's pretty easy. Yes, the creating header file for the batch processing is same as we learned in the last lecture. So I am not explaining the process in the detail. However, you should be very careful that we need to select no height for the map projection, which means you are not taking into account the height of the points, because it is a 2D map projection system. Moreover, so if you click on the create, so it will create a header file, and this is the example of the header file here. Okay, the procedure is same, and there you can see that this is my order which I selected here, that is longitude and latitude, and it is mentioning no height. That means we do not in fact need the height. However, it is saying geodetic coordinate system. it is two-dimensional geodetic coordinate system, what we call as geographical coordinate system. So now here we should be careful that this software is using word geodetic with no height to indicate the 2D geographical coordinate system. So this is the header file for input, and once I populate the header file with the data, it will look like that. So I am putting longitude and latitude in order for 10 points. Okay, so this is my input file prepared for the map projection. Now I will project this geodetic or the geographical coordinate of 10 points into some map projection, maybe UTM, LCC, polyconic, and so on. So that's the batch processing for getting the output. You go to the file, you select the input file which we have recently prepared in the last slide, and then you will select your output. That means in the output you are selecting UTM because you want to project your geodetic two-dimensional coordinates into UTM map projection X and Y. Fine. Once you click OK, so you will get this kind of interface where you will save the output file, and the moment you save the output file, there will be a message like number of coordinates processed. There are 10, and it is also giving you there are no warnings, there are no errors, and the time elapsed is minimum time. Well, now you can populate your input file with plenty of coordinate, and now you use it. In that case, you should wait for some time because this application will take some time to process your data because the data is in plenty. So now this was my input file, and here if I convert into UTM projection, you can see that it is the 46 zone here, 46 N zone, and this is my X coordinate and this is my Y coordinate of the UTM map projection for this zone. Now here I am doing the reverse process. That means I am converting my UTM map projection, which is given here in the input file with 46 N zone, and this is my X and this is my Y coordinate. Now I am converting back and I am getting this, which is 21.6 degree latitude, 11 second, 10.4 seconds, and north and east it is being shown here. So I read it again, 91 degree, 41 minute, 28.3 second east, 26 degree, 11 minute, 10.4 second north. That is the latitude and longitude information. Fine. So you can try yourself also. Here if you look at the header file, geodetic is the coordinate system, WS84 is my datum, ellipsoid is also WS84, no height, you see, and then coordinate order is longitude and latitude. Okay. Here in the input, if you see that universal transverse Mercator, which is already a map projection, see, and WS84 coordinate and ellipsoid. Here we are not saying that there is no height because we know that map projection system by default is a 2D projection system, but geodetic can be 3D or 2D, and that is the reason in case of geodetic coordinate system we say whether we have ellipsoidal height, whether we don't have the height. In case we don't have the height, so heights are not specified here in the output. Now coming to the geodetic coordinate system to LCC map projection. So what I am doing here is, this is my input file which I have already prepared, and now I am converting here. In case of LCC, you see it is one standard parallel, that is a tangent system. It is touching the surface of the earth at this standard parallel. So the central meridian is my this, and origin of latitude is this, scale factor, and then false easting and false northing. Since this LCC projection, one standard parallel or two standard parallel are user specified, so we need to specify false easting and false northing. In case of UTM, it has its own arrangement where UTM has some false easting and some false northing value, especially in the positive, like around 5 lakhs, and because of that we will never get any negative coordinate there. You see here, so geodetic coordinate system to LCC to parallel map projection. Okay, so you can see this is the interface here, and this is my output file which is shown up here, and this is the input file. You can see here there is a height information also, right, and here I am specifying ellipsoidal height. You will see the magic in the map projection. We don't get any height because the map projection does not use the height information at all. So even you specify the height, it is not going to matter for the map projection for this application. Okay. Now see here, this is the central meridian of first standard parallel. So this is my standard parallel 1, standard parallel 2, and again I am specifying false easting and false northing here. Okay, let us go ahead, and this is back. That means from LCC to standard parallels and map projection to geodetic coordinate system. So these are again input information I am providing, and I am getting this thing. So you see here there is no height, and that has been indicated here, no height. Okay, again now coming to the polyconic projection system, here the central meridian and origin of the latitude are there. I am converting the geodetic coordinate system to polyconic. So in case of polyconic, this is my output here, you see, and this is the input here, and again input is given with the height, which is not going to make any sense for this application. And see, since there is a false easting and false northing are 0, I am getting these negative coordinates. No worries, if you specify false easting and false northing as positive values, let's say 5 lakh, 5 lakh, you will get some positive values always. So you have to be careful when you choose some kind of particular application or particular map projection system. Okay, then you also learn how to write the header file, and it is pretty easy now. Okay, again back I am doing polygonic map projection to geodetic coordinate system. So that is the conversion is there. Again I am using with the negative values here, and you see that you will get all the correct values. This is degrees, minute, seconds, and again this is latitude value, degrees, minute, seconds. Okay, here you can read the header file for output, and this is the header file for input, the header information I can say, and these are the coordinates. Okay, now coming to the geodetic coordinate system to transverse Mercator map projection. Again remember that transverse Mercator is again user defined, and UTM is a specific example of transverse Mercator. So for that UTM we did not to define anything, but in case of any other projection we need to define. So that is my central meridian information and the output, since I am converting from geodetic. Again height, no meaning here, and central meridian is there in output, origin of latitude is there, so I get some kind of negative coordinates again here. So again use some value on the false northing here. Let us say if you specify 5 lakhs or maybe 50 lakh, you will get, so specify 50 lakh, you will get positive coordinates. So again back from transverse Mercator projection to the geodetic coordinate system. So only my input is changing and output is I am getting accordingly. Further now I am doing the map projection transformation, that means between one projection to another projection. Surprisingly here I am not changing my ellipsoid, that means still I am having the same reference frame. So within one reference frame I am using LCC map projection, and then I am converting that LCC map projection coordinates into, let us say, transverse Mercator or UTM or polygonic projection and so on. Fine. So what's the process going on at the back end? You see, from the LCC first it is converted to the geodetic coordinate system, and then from geodetic coordinate system it is converted to the UTM map projection. So let us see what's my input. So input, you can see header here, you have already written such kind of header, and there you will get the header of this thing. Well, you are getting the correct answers, you can match it and you can do it yourself also. That means you use this coordinate, this information, and repeat the exercise for yourself. Further you see the UTM map projection to LCC to parallel map projection we are doing here. Okay, so now we are giving the information, and automatically in the output this header will be created. But you need to specify your own information where you want to create the standard parallels and where you want to put your central meridian and origin of the latitude for LCC map projection to standard parallel. Going ahead, now I am doing the same example for LCC one parallel map projection to polyconic. Okay, so well, I have already shown one example, now I am putting it another example there. Only because of one standard parallel we have different information, slightly different information. We have information only for one standard parallel. So we have output here for according to the polyconic map projection here, right? Going ahead with LCC map projection to transverse Mercator, here when you specify in output the transverse Mercator, you need to specify this information, where do you want to put your LCC, the transverse Mercator origin and so on. So accordingly this application will do transformation for you. Now coming to the map projection with datum transformation. So let us see, there is a geodetic coordinate system, right, and it is being specified in WS84, and I am trying to convert into the LCC map projection of Everest 1830. Fine. So you see that input file is there, here input, and this is the longitude information lambda, this is my phi information, and this is the height information, which is of no use. But now I am going to convert this data into the LCC map projection with one standard parallel, and datum is Indian, that is Everest 1830, ellipsoid is Everest 1830, and this is the information I have specified on the Everest ellipsoid, not on the WS84 ellipsoid. So you have this information with central meridian and origin latitude. With this information, if I convert, I will get this kind of information here. That's my output. So now you can specify this information. Again, I am doing the same thing back. Okay, now LCC map projection, Everest 1830 to UTM map projection. Fine, we are doing all these possibilities we are trying to cover. But remember, generally we have LCC map projection for the Everest ellipsoid. That means UTM projection can be defined for the Everest ellipsoid, but LCC map projection is not preferred for WS84 ellipsoid. So if you just specify this information again, you will get this kind of output. Okay, and this is the interface on the left hand side I am showing. Now it is a reverse one. That means I am using UTM map projection for WS84 in input, and I am trying to convert the coordinates in LCC map projection with Everest ellipsoid. So these are the sources of the map. So with this I can say that now you are able to do all the map projections. You are also able to do coordinate transformation. You are also able to do datum transformation with either reference system or with map projection. So here we finish this module on reference system, coordinate system and map projections. In the next module, we will go for astronomy and time. Till then, bye bye. Thank you for attentively listening.